Okay, it must be 15 minutes. Okay. Good afternoon. I'm Motomichi. I'm from Tokyo University, IMR. Keyword is marked by red. This time I talk about hydrogen effects on micro damage in HCP martensite. This is a bit different from typical BCC martensite. So let's start the talk from the multi-phase steel. Unlike the single-phase steel, for example, the ferrite martensite dual-phase steel, this material also shows the hydrogen embrittlement. But the point is usually this material shows hydrogen-assisted failure after the significant plastic deformation. Why it is so is once damage, that means void or a crack, is arrested even with hydrogen. Therefore, the damage doesn't grow rapidly even in hydrogen. Therefore, when we investigate the hydrogen embrittlement in multi-phase steel, like BCC, martensite ferrite, or austenite ferrite, duplex steel, anytime, we always must check the crack growth behavior. Then, what I would like to stress in this talk is HCP. Why HCP? Okay, for example, the type 304, it shows a BCC TRIPS effect. Then it shows a good elongation and the strength. Actually, the HCP also shows a good elongation, like the BCC TRIP effect. Now, furthermore, in a hydrogen case, HCP has a good point. That means diffusivity is lower than BCC, even than FCC. But probably most of the audiences already know that HCP is not so good because HCP structure has always anisotropic in terms of elasticity as well as plasticity. Then it's usually the cracking is induced. But anyway, HCP martensite is very important to understand the underlying mechanism of plasticity, even for the BCC TRIP. Usually, such a BCC martensite forms after the formation of HCP. Then also, this is the case of iron 28 manganese that doesn't show BCC, only shows the deformation-induced HCP martensite transformation. This case, okay, it didn't show the brittle fracture. Then it shows over 50% with a high tensile strength. Therefore, when the martensite lattice constant is optimized, then even with the HCP, it can show the good property. But always, problem is, as I mentioned, such a micro damage. As we predicted, when HCP forms, even without hydrogen, such a nanovoid and subsequent coalescence results in large damage. Then it deteriorates local elongation. It's always a problem. Then we can easily predict that hydrogen, when hydrogen is introduced, then deterioration is observed. Then as easily expected, such a cracking were induced. Okay, it's a bit well known. But the point is, such a micro damage behavior is always very important because HC martensite sometimes is not avoidable. Like, for example, twip steel or authentic steel. When the material is deformed with a slightly low temperature, then HCP easily forms. Then again, maybe audience says that, okay, it can be avoided by the chemical composition design. However, usually the authentic steel is optimized for the tensile ductility without hydrogen. Then, usually the authentic steel must have low stacking Ford energy. Otherwise, it's just a low strength, low elongation material. Therefore, in terms of high strength authentic steel, we always must care the HCP martensite. Then, this talk, I would like to present the result of quantification of microstructure and micro damage evolution behavior with an effect of hydrogen. Actually, this has not been clarified so far. Then let's raise some possible hydrogen effects on the damage evolution associated with the HCP martensite. As an intrinsic factors, hydrogen affects mobility of slip and transformation dislocations. Then such a difference in relative mobility of transformation dislocation and slip dislocation can change the transformation behavior, particularly in the HCP martensite. The next one is, okay, hydrogen is a kind of the alloying element, regarded as alloying element. Therefore, the free energy of HCP and FCC also can be changed. Then a promotion, sometimes suppression can be induced. Then a final one is, as a most important factor of embrittlement, hydrogen deteriorate the resistance to cracking, probably associated with the epsilon martensite plate. Then based on such intrinsic factors, what we can measure, always a quantification is very difficult. This study, we try to investigate the resistance to damage initiation and growth by counting the number of the damage, size of the damage, or area of damage. Then next one is the martensite fraction. It can be quantified by XRD or EBSD. It's not so difficult. Then final one is the martensite morphology. Second phase, always, okay, just phase fraction cannot determine the internal stress. Always we must care the morphology of the microstructure. In case of the HCP, it is a plate type martensite. Therefore, the thickness is one of the most important morphology that can control the internal stress or local stress. Then these are quantified in this study. Then we selected the material that can show the deformation-induced HCP martensite transformation without pre-existing HCP martensite. Then hydrogen was charged at 100 megapascal. Then strain rate was relatively low room temperature. Then with this condition, the introduced hydrogen concentration was 27. Just it's a number. Then this is the result. Okay. Even with hydrogen, the failure occurred after 18%. Okay, it's a significant plasticity. Then point is what happens during 18% plastic strain with the presence of hydrogen and epsilon martensite. This is a fracture surface. You see, even in uncharged case, it shows a quasi-cleavage fracture. That is usually discussed, interpreted as a epsilon martensite related to cracking. That is along the gamma epsilon interface. But actually, it's a bit complicated. Such a quasi-cleavage fracture is induced by the martensite twin boundary interaction, martensite grain boundary interaction, and the martensite interaction. Usually, these three interactions can cause such a quasi-cleavage fracture. Then by hydrogen uptake, the quartz cleavage fracture feature got more distinct. Then in general sense, we can simply think that, okay, epsilon martensite related cracking was promoted. Then let's see the detail. Okay, then just we counted the area fraction, number of the damage, and size. Then first we noted the number density of damage. Then we just counted 1, 2, 3, 4, 5 using the just normal software. Then we plotted the number of the damage in number density of damage against the strain. Then near the fracture surface, it has a large strain. Then a grip part has a 0 strain. Therefore, we can plot the damage data against the wide range of the strain. Then I see here, the most important point is the number of damage dramatically increased. Damage initiation was promoted. Then, irrespective of the strain, always a huge damage were observed. Then the damage initiation sites were observed like this. Then, as I mentioned, in the case without hydrogen, okay, interaction is very important. Interface martensite interaction. Similar to the case without hydrogen, the hydrogen charged specimen also showed a nanovoid along twin boundary that impedes the epsilon martensite, also grain boundary, and within epsilon martensite. But always the damage size is very tiny. Such a very small nanoscale nanovoid forms everywhere. More specifically, there are even just after yielding, such a nanovoid forms. In terms of average damage size, as I mentioned, just similar to the other multiphase steels, damage arrest, that means the size once remains constant, then start to increase, then a failure. Point is, okay, even with hydrogen, damage was arrested somewhere. But the damage arrestability, that means the range of the strain where the damage size constant, is decreased, shortened by hydrogen uptake. Then now let's see the damage growth behavior. It's a bit dark, but here we can see one crack. Okay, this is crack. But magnify, we can see like this. Still looks crack. Then further magnify. Here, please see here, it's not cracked. In front of the crack tip, there are numerous nano voids. Therefore, this is very important point. Even for the damage growth, the hydrogen-assisted damage initiation, that means nanovoid formation, controls the damage growth. Always when the deformation or stress level is severe, for example, particularly at the crack tip, then such a nanovoid forms. It is a bit self-evident because when the situation is severe, then numerous martensite forms. Then with increasing the martensite fraction, okay, maybe damage is easily formed. But the point is, we must be more careful. Okay, just nanovoid formation is accelerated. We must point out why such a promotion is caused. Then, okay, one is the cohesive energy of the interface, but the other one is the martensite fraction. By hydrogen charging, then martensite fraction increases. It means nanovoid initiation site probability increases by hydrogen uptake. That is one factor. Then another one is the Martin site. We just counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 grains were counted. Then we plotted the number of Martin sites per area against average thickness. Then in case of the hydrogen charging specimen, then always the Martin site thickness was below 2 micrometer. On one hand, depending on the crystallographic orientation, some Martin sites show the thicker in uncharged one. That means hydrogen decreases the thickness of Martin site. That causes an increase in local stress, for example, at the tip of the Martin site plate. Therefore, the hydrogen, facilitates the nanovoid formation, increase Martin site fraction, then increases the nanovoid formation probability. Then thin Martin site plates, it can provide a local driving force further. Then hydrogen deteriorates damage arrestability, resulting in the significant hydrogen effect in the HCP. It's a bit pity, HCP is not so good. Not good. But why I wanted to present this result here is suddenly the story changes. Shape memory effect. Do you know shape memory effect? It's deformed. Then by heating, shape recovers. It's called the shape memory alloy. Actually, the HCP Martin site is an origin of shape memory effect. Such a forward and reverse transformation can provide a shape memory effect. Then the point is, we measure the shape recovery strain. Then we just measure the recovery strain using the same material that were used for this study. Then this is the results. Then this is very happy results. I love HCP Martin site. Point is, without hydrogen, recovery strain increases with increasing the pre-straining. Then finally, it's reduced because of the introduction of the slip deformation. Since Martin site fraction increased, then shape recovery property was improved. It's great. Then just please note that. See here, failure doesn't occur until the 18%. Therefore, the pre-strain of 8% or 10% doesn't matter. Then even when considering the nanovoid, until the 0.1 strain, this is case of true strain, but it's mostly the same as the nominal strain. Still, most of the damages are arrested. Therefore, the failure doesn't occur at around 10%. That means hydrogen can be used as a new alloying element that can improve the shape memory alloy. That is what I wanted to say. Thank you for your attention.